Hello and welcome back. We are on the second lecture of Introduction to Glass Science. If you remember, last time we actually started at the end of the book, chapter 23 of Fundamentals of Inorganic Glasses, third edition. Last time we covered various applications of glass. So this includes things like architectural glasses, glass optical fiber, fiberglass, glasses for packaging, glasses for information display. And we discussed all the many ways that glass has brought modern civilization to what it is today. And we also took a look into the future to see what future applications glass might have to offer. Today, we are going back to the beginning of the book. We're going to go back to chapter 1 and discuss glass compositional families. The purpose of today's lecture is to try to give you a broad overview of various compositional families of glass, including some of their important properties. And then what we'll do later in the course is to dive in deeper into each of these families to learn about their structure, to learn the details of their properties, and so on. So let me share my screen and let's dive into this. So lecture 2 is glass compositional families. If you are following along in the book, which I recommend, please be sure to read chapter 1, which corresponds to this lecture. All right, so let us start with commercial glasses. This is a picture of the Shard, which is the tallest building in London. One of the distinctive features of the Shard is not only is this shaped like a shard of glass, but the entire outside of the building is encased in glass. It's a beautiful building. Definitely, if you go to London, please take the opportunity to go up to the top of this tower. It has a beautiful view of the city. But the reason I bring this up is that when it comes to commercial glasses, as we saw last time, nearly all of the commercial tonnage of glass consists of oxide glasses. That is, glasses that have oxygen as the anion in the composition. And of those, by far the largest percentage of these oxide glasses are silica-based glasses. These are glasses that have silica, SiO2, as their primary constituents. And this includes both commodity glass products as well as highly specialized applications of glass. And what this means is that for like the everyday person, if you just use the word glass, usually the image that comes to mind is an oxide glass and specifically a silicate glass. What are some of the features that make silicate glasses so ubiquitous? They are low cost because they're made of commonly available minerals that are in the Earth's crust. They are optically transparent, they are mechanically strong, and they're chemically very resistant to corrosion. And for all of these reasons, silicate glasses have been the dominant family of glasses. That being said, there are many more different glass families, and we're going to cover several different types of glass compositional families in this course. And to give you kind of a one slide snapshot of the US glass industry, glass is very important on its own as an industry, but also has a huge impact on other industries. So this image actually comes from the US Census Bureau. And in the middle here, it's listed as high performance glass and glass product manufacturing. And from the middle here, the glass industry itself in the United States accounts for about 76,000 employees spread out over about 1,500 companies, the vast majority of which, 95%, are small and medium enterprises. And in total, the glass industry produces over $20 billion of shipments per year. So the glass industry itself is a very important part of the US economy. But what's even more important is if you consider the impact of glass has on so many other industries, whether it is the glass that's used in consumer electronics, armor glasses for defense application, glasses for energy storage, transportation, renewable energy, optics, lighting, information technology, biomedicine, and building materials. These are all impacted industries where glass plays a critical role. And if you consider the value of all of these industries that would not exist without glass, the total impact of glass on the US economy is closer to about 1.8 million employees, affecting about 55,000 companies, 98% of which are small and medium-sized enterprises. And then the total impact of all of these industries that rely upon glass is about $830 billion per year. So glass is an essential and often overlooked part of the U.S. economy and the global economy as a whole. So let's start off with what might be considered the simplest glass, but also has a lot of hidden complexity in it, and that is vitreous silica. Recall from last time that the word vitreous is synonymous with glassy. So when we say vitreous silica, that's the same thing as saying silica glass or glassy silica. Vitreous silica is composed 100% of SiO2. It is 100% silica. And some of the properties of vitreous silica are, first of all, it is the most refractory of all commercial glasses. By most refractory here, this word refractory is not referring to the refractive index, but rather it is referring to the temperature resistance or the thermal resistance of the material. A material is said to be refractory if it is able to withstand very high temperatures, and silica is the most refractory of all commercial glasses, meaning that it can withstand the highest temperatures of any commonly available types of glass. Vitreous silica also has very high resistance to chemical corrosion. It also has a very low electrical conductivity, which means that it is suitable for applications where a high electrical resistance is required. It also has an exceptionally low coefficient of thermal expansion. It's on the order of 5.5 times 10 to the minus 7 per degree C. This means that the dimensions of vitreous silica change by very little with respect to changing temperature. And for these reasons, because of the very low thermal expansion coefficient, and the very high temperature resistance, vitreous silica is the material of choice for the windows on space shuttles. Silica also has a good ultraviolet transparency. So you can see here that it is highly transparent in the visible, and it also has good ultraviolet transparency and good transparency in the near infrared as well. The downside of vitreous silica is because of its really a well-connected glass network, it requires very high temperatures in order to produce this. And that means that it has a fairly high cost of manufacturing. Even though the raw material, SiO2, can be made from quartz sand, in order to melt the quartz sand, you need to get to temperatures above 1800 degrees C. And if you want to make it with good enough quality, the temperatures have to be in excess of 2000 degrees C. So because of this, it is very expensive to manufacture. That being said, it is an essential material for applications such as astronomical mirrors, optical fibers because of its exceptionally high transparency. It's used as a crucible material because of its high refractory nature, and is also used for high efficacy lamp envelopes. So despite these costs of manufacturing, it is a really essential material for a wide variety of industries. Most vitreous silica nowadays is not made by melting quartz. Rather, it is made by a chemical process where silicon tetrachloride, SiCl4, is reacted with oxygen gas in order to form silica vapors that get deposited onto a preform, and then they get consolidated into a solid piece of vitreous silica. And so all optical fibers nowadays are actually made by this chemical route rather than by melting quartz. This leads to higher quality because there aren't any impurities that you might find in quartz sand. And so this is what ensures the best possible optical performance. We are going to return to vitreous silica a bit later in the course. For now, just know that this is the simplest glass in the sense that it has only one chemical component to it, SiO2 or silica, and know some of its key properties, including its high heat resistance, very low thermal expansion coefficient, very low electrical conductivity, and high chemical corrosion resistance. Now, in order to deal with this problem of the very high melting temperatures of silica, what people have done for centuries is to add other components to silica. And the most common silicate glass is soda-lime silicate. Soda-lime silicate accounts for something like 90% or more of all commercial glass production. Soda-lime silicate is by far the most widely used glass. This is used for essentially all beverage containers, food containers, architectural windows, glazing that is in automobiles, fluorescent lamp envelopes. All of these are made from soda-lime silicate glass. Soda-lime silicate is made by taking pure silica and adding two additional components to it. Soda ash is added. This is sodium carbonate, and limestone, which is calcium carbonate. When those are melted, they convert into oxides and releasing carbon dioxide in the process. And this is actually one of the main challenges of the glass industry right now is how to reduce carbon emissions by eliminating soda ash and limestone. Because, though, of the addition of sodium oxide and calcium oxide, the sodium and the calcium act to break up some of the conductivity of the glass network, and this lowers the temperatures that are required for melting. So as a result, instead of going to 2000 degrees Celsius, as you do with vitreous silica, soda-lime silicate can be melted at much lower temperatures, on the order of 1400 to 1500 degrees C. And what this means is that it's much more convenient and lower cost to melt soda-lime silicate glass compared to vitreous silica. And as a result, this is why soda-lime silicate is so ubiquitous in our everyday lives. Some of the key properties of soda-lime silicate glass are, first of all, it's low cost. So it's made primarily from soda ash, limestone, and quartz sand, all of which are abundantly available in the Earth's crust. So these are low-cost raw materials. By lowering the melting temperatures, this also lowers the cost that is associated with actually making the glass. Soda-lime silicate also has a very good chemical durability. It's not as good as vitreous silica, but it is good enough for everyday applications of glass, such as in beverage containers, glass windows, and so on. And it also has a good enough optical transmission in the visible regime to be used for windows, jars, and so on. So if you just look through the thickness of a window, it appears to be nice and transparent in the visible. If you take a window, though, and you turn it on edge and try to look through the width, what you'll notice is that the glass is actually green, and that is because of trace amounts of impurities that come from iron oxide. Because these raw materials are dug up from the Earth's crust, one of the most common contaminants is, in fact, iron oxide, and that's what gives a greenish tint to soda-lime silicate. So this means it's fine if you're just looking through a fairly short distance, like with a window, but soda-lime silicate is not suitable for transmitting light over long distances, such as optical fiber. So that's why we need vitreous silica to make optical fiber for transmitting light over hundreds of kilometers. The other downside of soda-lime silicate glass is that it has a much higher thermal expansion coefficient compared to vitreous silica. Remember from the last slide that the CTE of vitreous silica was 5.5 times 10 to the minus 7 per degree C. With soda-lime silicate, it's 95 times 10 to the minus 7 per degree C. So it's a significantly higher thermal expansion coefficient. And what this means is that if you take soda-lime silicate and subject it to thermal shock, it's much more likely to break compared to fused silica. So, soda-lime silicate is good because of its low cost. It has decent optical transparency. It has pretty good chemical durability, but the Achilles heel is often the high thermal expansion coefficient. So to solve this kind of Goldilocks problem here between fused silica or vitreous silica and soda-lime silicate glass, borosilicate glass was developed back in the late 19th century by Otto Schott, and this gives us a thermal expansion coefficient which is in the middle. Depending upon the exact composition, the thermal expansion coefficient can be between 30 and 60 times 10 to the minus 7 per degree C. Most of the commercial borosilicate glasses fall at the low end here of around 30 times 10 to the minus 7 per degree C. So the thermal expansion coefficient of borosilicate glass is about a third of that of soda lime silicate, which means that it has about 3 times better thermal shock performance compared to soda lime silicate. The way that AutoShot was able to develop this glass is by removing a bunch of the sodium oxide from soda lime silicate, also removing some of the calcium oxide, and replacing it with boron oxide. Boron oxide is able to lower the melting temperature of the glass compared to vitreous silica, although it's not as effective at lowering the melting temperatures compared to sodium or calcium. It can bring the temperatures down to about 1600 degrees C or 1650 degrees C, which is a lot cheaper and easier to deal with compared to vitreous silica, although not as low as soda lime silicate. So borosilicates are kind of falling somewhere in between soda lime silicate and vitreous silica in terms of the temperatures that are required for melting, in terms of the cost of manufacturing, in terms of properties like thermal expansion coefficient, also chemical corrosion resistance. Borosilicate glasses tend to have better chemical corrosion resistance, so they are more highly resistant to chemical attack compared to soda lime silicate, although they're not as good as vitreous silica. So for now, you can think about borosilicate glasses as kind of occupying this middle ground between vitreous silica and soda lime silicate. As a result, borosilicate glasses are commonly used in laboratory glassware. Just about all the glasses that you will see in your chemistry lab are made from borosilicate glass. A large fraction, probably the majority of pharmaceutical glassware is also borosilicate glass because borosilicate glasses have high corrosion resistance, but are also lower cost compared to vitreous silica. So that makes borosilicate glasses the glass compositional family of choice for pharmaceutical applications. Borosilicate glasses are also used for automobile headlamps because of the high temperatures that they have to endure. And therefore, the better thermal shock resistance gives them a performance advantage compared to soda lime silicate. The improved thermal shock resistance is also important for laboratory glassware because if you put these glass flasks or beakers over a Bunsen burner, it has to be able to withstand pretty abrupt changes in temperature. And one final common application of borosilicate glasses is in household cookware. If you have glass baking dishes, those were all originally made from borosilicate glasses. And in fact, Corning's version of borosilicate glass, which was sold under the trade name of Pyrex, first gained widespread adoption in people's kitchens as use for glass bakeware. This was used for glass bakeware because of its high thermal shock resistance, meaning that you could have your hot glass pan in the oven, remove it quickly from the oven, and make sure that it was not going to break. That being said, one needs to be very cautious nowadays because more recently, at least here in the US, the company that has been selling glass cookware under the trade name of Pyrex is not actually selling borosilicate glass. They are selling soda lime silicate glass and marketing it as Pyrex. And so as a result, the thermal shock resistance is about 3 times worse. And this has led to several unfortunate accidents with glass bakeware shattering as it comes out. In Europe, there are laws against this, and in Europe, it must be true borosilicate glass because of this reason. So if you want to get borosilicate glass cookware, be sure it is labeled as such. Or if you go to find some like old antique glass bakeware, chances are that that is probably made out of borosilicate glass and is a true Pyrex rather than a soda lime silicate glass. So please be careful about that. The next major family of silicate glasses are lead silicate glasses. Lead silicates contain lead oxide and silica. Lead, as you probably know, is a very large element. That means that it has a large number of electrons, which means that it raises the refractive index of the glass. Lead silicate glasses are better known by the name crystal. They are called crystal or crystal glass because of their high refractive index, which gives them this optical brilliance. This causes them to bend the light more and gives it kind of a sparkle that some other glasses are lacking. That being said, the name crystal is a misnomer because, as we're going to learn in this class, glass is defined as being a non-crystalline material. So this name crystal is really not an appropriate name for lead silicate glass, and the name like a crystal glass is actually an oxymoron because a glass is defined by being non-crystalline and therefore cannot be a crystal. But just so you know, people who are not taking this course and don't have that scientific understanding may refer to this as simply crystal. And what that means is that it has a high concentration of lead oxide. Some of the key properties of lead silicate glasses are the high degree of brilliance. This is used in stemware. It's used in this case this is Steuben glass, which is Corning's or was Corning's line of lead silicate glasses. Uh, it has a very large working range. So artists really love working with lead silicates because they can work with it over a large temperature range. And what this means is that it's actually a beautiful medium for art. From an engineering point of view, lead silicates are also known for their high electrical resistivity, so they're good for electrical feed-through components. The main problem of lead silicates should be obvious, and that is the toxicity of lead, which makes it very dangerous to deal with the raw materials and to deal with waste that comes from, say, grinding or polishing of lead silicate glasses. And as a result, many of the companies that make this, crystalware, investigate alternative formulations that don't involve using lead silicate. The best replacement for lead oxide would be barium oxide. So barium is mostly non-toxic and it has maybe perhaps a small degree of toxicity, but nowhere near the level as lead oxide. Barium also increases the refractive index of the glass. It's also really good for improving the working range of the glass. It's not as good as lead oxide in any of those respects, but it is fairly non-toxic and is a preferred substitute for lead oxide. Next up are aluminosilicate glasses. Aluminosilicate glasses are highly versatile. Aluminosilicate glasses involve incorporating alumina, or Al2O3, into your silicate glass matrix. Usually they also incorporate some alkali oxides or alkaline earth oxides, like sodium oxide or calcium oxide. Aluminosilicate glasses have been the compositional family for a wide range of advanced engineering glasses, including, for example, the Gorilla Glass that is probably on the cover of your smartphone. In this case, aluminosilicate glasses are chosen for their very high strength and the ability to chemically strengthen the glasses, which is something we'll get to towards the end of this course. Aluminosilicate glasses here have high resistance to the introduction of damage, whether it is scratching damage or indentation damage. Aluminosilicate glasses, when made really thin, can also be bendable. So this is called willow glass. This is a very thin bendable glass that can be used for flexible displays. So this has a high strength together with bendability. Aluminosilicate glasses are used as the substrate for flat panel displays, whether it is the screen on your smartphone or the screen on your laptop computer or TV. Those all contain aluminosilicates glasses to build the display onto. Aluminosilicates are also made into fiberglass. These are used for fiberglass insulation because of the ability to be formed into fibers and because of the high temperature resistance of aluminosilicate glasses. And aluminosilicate glass fibers can be incorporated into composites too, using a polymer filler. And fiberglass is actually a great material for making vehicles from. So this is a Corvette. Corvettes are known for their lightweight and high speed, and also, of course, the beauty of the car itself. And all of that is made possible by the use of fiberglass. Fiberglass is also the material of choice for making most boats nowadays. So the lightweight of the fiberglass, the high strength, the resistance to attack by water, all of these properties make fiberglass the material of choice. Now, getting beyond silicates, there are many other types of oxide glasses that don't involve silica. An oxide glass is any glass that is based on having oxygen as the anion. And many other families of silica-based glasses exist. And we have both oxide glasses that incorporate silica, as well as oxide glasses that don't incorporate silica. Some of the other components that we can add include barium oxide, as I mentioned. This was to increase the refractive index of the glass. Zinc oxide is another component that is sometimes used. Lanthanum oxide, neodymium oxide. These can make fluorescent glasses. This is an example of a fluorescent rainbow that one of my friends made here. And this, when you expose it to ultraviolet radiation, will fluoresce at different wavelengths in the visible. And so other types of silica-based glasses with other components can give these optical glasses. And when we move to non-silica-based oxide glasses, these are glasses that are based on oxides such as B2O3, which is borate, P2O5, phosphate, V2O5, vanadate, GeO2, which is germanate, or TeO2, which are tellurite glasses. So non-silica-based oxide glasses can be made from any of these oxides shown here. Borate glasses are really interesting because of their low melting temperatures. On the downside, they tend to have poor corrosion resistance, but sometimes you can take advantage of that poor corrosion resistance. For example, B2O3-based fibers, borate glass fibers, have been used to have a medium to promote soft tissue repair. This shows a close-up image of borate glass fibers that if you zoom in, it looks like this. If you zoom out, it looks kind of like cotton candy. And these have been developed to help treat diabetic patients that have open soft tissue wounds, that when these fibers are packed into the wounds, they help to stimulate the body's natural healing process while keeping an antimicrobial environment. And as they corrode, as they degrade and dissolve into the body over the course of a few days, they are delivering the chemicals that the body needs to help repair itself. So this is a case where actually the poor corrosion resistance of the borate glass fibers can be used as an advantage because as they degrade, they deliver the chemicals that the body needs. Phosphate glasses are used as laser host materials. These are used because of their special optical properties and because of the ability to incorporate a large amount of rare earth oxides into the phosphate-based glasses, which make them really good materials as laser hosts. Vanadate glasses are known for their low temperatures. And germanate and tellurite glasses are also known for their high refractive indices. Now, another family of non-crystalline materials are amorphous solids. I want to say up front that one needs to be very careful here with terminology because amorphous solids are not glasses. Glasses and amorphous solids are thermodynamically distinct classes of material, and we will understand why when we get to the next chapter of the book, chapter 2. But for now, just know that many semiconductor elements here, such as silicon, germanium, phosphorus, and arsenic, as well as compounds, such as this cadmium, germanium, arsenic compound here, these can be deposited through vapor deposition and form amorphous structures, meaning that they have non-crystalline structures but are distinct from that of glassy states, as we'll learn more next time. But for now, just know that amorphous semiconductors exist, and that these are critical materials for use in thin film transistor TFT displays. They are critical materials for solar cell applications, especially amorphous silicon. Amorphous silicon is really the most commonly used material in photovoltaics. So if you have a solar cell, most likely it's probably made from amorphous silicon. Next up are chalcogenide glasses. So if you go down the periodic table from oxygen, the next element going down from oxygen is sulfur, and then selenium, and then tellurium. So if instead of having an oxide glass, if you have a sulfide glass, a selenide glass, or a telluride glass, these are called chalcogenide glasses. And as you move downward in the periodic table, the anion here is becoming larger and larger. So sulfur is larger than oxygen, selenium is larger than sulfur, and tellurium is larger than all of them. As these elements get larger, it actually pushes the low loss optical transmission window out to longer and longer wavelengths. So this shows, for example, silica here having very high optical transmission across the visible wavelength. As you go to sulfides, this low loss transmission window is being pushed to longer wavelengths into the near and the mid infrared. As you go from sulfides to selenides, this pushes out farther into the infrared, into longer and longer wavelengths, and tellurides can transmit into much longer IR wavelengths. But what you'll notice here is that if you look at the transmission of the visible, instead of silica, which is very transparent in the visible spectrum, sulfides tend to have a yellowish color, selenides tend to have kind of a reddish color. Tellurides appear to be black in the visible because if you look here in the visible spectrum, they are not transmitting visible light anymore. So this image here in the lower right shows what it looks like if you look through a telluride glass in the visible range of wavelengths, where you cannot see through it because it's not transmitting the light. However, if you use an infrared camera, you can see that the telluride glass is in fact visible in the infrared. And so you can see the heat here, the infrared rays traveling through the telluride glass. So chalcogenides are used for infrared properties. The next family of non-oxide glasses are metallic glasses. This is one of the newer families of glasses. These were discovered about 60 years ago. And metals are actually very easy to crystallize. Things like iron, copper, they very readily crystallize. But if you were to make alloys that have enough different metallic elements in them with different types of crystal structures that they prefer, one can kind of leverage the alloy's inability to form a single crystal in order to stabilize these metallic alloys in the glassy state. So in other words, if you're able to have a liquid alloy of many different metals and then cool that liquid alloy fast enough to avoid crystallization, you can actually freeze in a non-crystalline structure of the metallic alloy. And this is what's known as a metallic glass. A metallic glass is a metal, but with a non-crystalline structure. The initial metallic glasses could only be made into very thin sheets because they had to be quenched so quickly. More recently, new alloys have been developed to have what's called bulk metallic glasses, or BMGs. These are metallic alloys that can be cooled more slowly to form larger pieces. So metallic glasses are known for their lack of any type of crystal structure, which means that they don't have any crystalline grains. Most metals are polycrystalline, which means they have a grain structure, which means they have a roughness to their surface. In contrast, metallic glasses can have atomically smooth surfaces. One of the most common questions that I get about metallic glasses is, are they transparent? No, they're not transparent. They are optically opaque because they are metals. And because of their optical opacity. This means that they're not used in a lot of applications that we normally associate glasses. So metallic glasses are still trying to find their application space. Now, the newest family of glasses that have been developed are metal organic framework glasses. These are very interesting because they start off with a structural motif that is very similar to silica here, which is this tetrahedron. But instead of having these oxygens as the anions, there are imidazolate linkers here, these organic ligands, either imidazolate here or benzimidazolate. And these are essentially organic molecules that act to link the cation together. So instead of silicon with these metal organic framework glasses, they can be made from zinc or from cobalt. And then instead of oxygen, it has these organic ligand units. But you can see that the main structural motif is actually very similar. It's a tetrahedral unit where the cation here is, instead of silicon, it's zinc. And instead of being bonded to 4 oxygens, it's bonded to 4 organic ligand units. Some of the interesting things about metal organic frameworks are that A, it's optically transparent. B, it's got a very high Poisson's ratio, above 0.4, which means that it might have higher fracture toughness compared to some other oxide glasses. And thirdly, they're actually really stable. They have a glass stability, which is similar to that of vitreous silica. So that's kind of a brief survey of many of the human-made glasses. I want to spend the latter part of this lecture to cover some naturally occurring glasses. Glasses have existed in nature for as long as the Earth has been around. One of the most common natural glasses is obsidian. Obsidian is volcanic in origin. Here you can see a picture of obsidian. This comes from volcanic eruptions where the lava that comes out is cooled into obsidian, and this is a glassy material. A typical chemical composition of obsidian is about 75% silica, about 13.5% alumina. It has a high amount of iron in it, which is what gives it the black color here. A little bit of calcium oxide and some alkali oxides such as sodium and potassium. And it's also common to have some manganese oxide in obsidian. And what this means is that obsidian is just another good member of the alkali aluminosilicate family. Obsidians also tend to incorporate quite a bit of water into their structure because of their natural origin. Obsidian has been used for a long time because of its high hardness, high strength. It can be made into sharp objects for use as tools. It's actually a very interesting natural material. Another type of natural glass is the fulgurite. Fulgurites are made when lightning strikes the soil. So when lightning strikes the soil, it can locally melt some materials that get quenched into the glassy state. These are some examples of fulgurites that are available right here at Penn State in our Museum of the College of Earth and Mineral Sciences. So be sure to head over to the museum if you're on campus here and check out some of these fulgurites. You can also find a nice exhibit of these at the Corning Museum of Glass in Corning, New York. Another family of natural glasses are tektites. Tektites are natural glasses that form as a result of meteorite impacts. There have been many different types of tektites found throughout the world. This shows what's called the Libyan desert glass. You can see that this is probably quite low iron because of the low color in this desert glass. Here is an Australasian tektite, which is very high iron, which is what gives it the black color here. In fact, the composition here of these Australasian tektites are, it's about 75% silica, high alumina again, but with an iron level that's about 4%. So this is very high iron. These are believed to be about 700,000 years old. The specimens that have been found around the world are about 1 to 2 centimeters in size. Other types of tektites include the moldavites, which are pale yellow in color or yellowish green. These are estimated to be about 15 million years old. And then this Libyan desert glass, which is pale yellow. And this is interesting because it contains about 97% silica and is about 28 million years old. So there is still ongoing debate about where the material comes from for making these tektites. Some believe that the material traveled to Earth on the meteorites and that this is of extraterrestrial origin. Others believe that the energy from the meteorite impact actually locally melted some of the sand and other materials, and then it quenched into the glassy state. So it was really more of the high thermal energy from the meteorite impact that created the glass using materials here on Earth. Next up is lunar glass. So various lunar glasses have returned from the Apollo expeditions. These include irregular fragments, spherules, teardrops, and dumbbell-shaped fragments of glasses. Some have been as small as a few microns, others millimeters in size. These are glasses that were found on the moon as a result of both lunar volcanic activity and meteorite impact on the moon. Some of these example compositions cover actually a pretty broad range. They tend to be lower silica than the natural glasses found on Earth, about 38 to 50% silica, higher in alumina, very high iron content, and also with some alkali oxides and alkaline earth oxides, and an appreciable amount of titania as well. Some lunar glasses have had as high silica as 89%, and because of the very high iron concentration, the glasses are quite dark in color. This shows an example of some lunar glass from the Apollo 17 mission. Finally, here I want to conclude this lecture with our next glass grate slide. Today, this is Norbert J. Kreidel, who lived from 1904 to 1994. Dr. Kreidel was born in Vienna, Austria in 1904, completed his PhD in physics at the University of Vienna in 1927. He worked in the glass industry in what was then known as Czechoslovakia for 10 years. But with Hitler's reign of terror that came, he and his family needed to flee to Czechoslovakia. He and his wife Melanie came to the United States in 1938 with, as he reported it, only $13 and a baby. So they arrived actually right here in State College, Pennsylvania. Kreidel found a job teaching at Penn State University. And from then he moved in 1943 to Bausch and Lomb, which is an optics company in Rochester, New York. He spent most of his career at Bausch and Lomb, where he became the director of materials research and development. And after he retired, he returned to academia and taught some of the next generations of glass scientists, first at Rutgers University and then at University of Missouri-Rolla, which today is known as the Missouri University of Science and Technology. Kreidel has a lot of great papers on glass structure, properties, and technology, and there is an award that is presented each year named in his honor. This is an award given out by the American Ceramic Society's Glass and Optical Materials Division for best graduate student research. So Kreidel was very passionate about teaching and especially about interacting with students. So it's very fitting that this award was made in his honor. All right, thank you for tuning in. Next time, we are going to move on to chapter 2, and we're going to discuss what it means to be a glass, and we're going to get to a specific definition of glass. So thank you for joining in. If you have any questions, please feel free to leave a comment below. Thank you very much.